All right, spring 2017 exam 1. First one of, there used to be 4. Maybe they still are. It's been a little while. Uh, Question 1, this is a very common question 1 you'll get. Just the domain of a function. So you're just trying to figure out what x values, like if you plug in an x value and it ends up being undefined, or you get like an imaginary number, that is outside of the domain. So you're just looking for the values that you can plug in. So you'll be looking out for things like if you do a square root, you know that you can't do like, square root of -1 or any negative numbers. So whenever you have a square root, you'll just set whatever's inside to greater than or equal to 0, give x by itself, and then that's part of the domain. It's one of its restrictions. So we'll be doing things like that. Uh, Looks like in here, the 2 that we have to worry about is the denominator. You can't divide by 0, and the square root can't take square root of a negative number. So let's do the denominator first. You can do them in any order, but let's just do this one first. Uh, so you can't divide by 0, so we're going to take the denominator and set it uh, not equal to 0. So one of these, and then we'll just solve for x, in which case we're actually going to get 2 if we take out an x. We get x times quantity of x minus 1 is not equal to 0. So then we know that x cannot equal, on this side it's 0, and on this side it's, let's see, if we plug in a 1, that'll make this 0. So can't be 0 or 1. So that's the first 2 parts of our domain, actually. You can have any number of parts, but usually it's about 2 or 3. So uh, x cannot equal 0 or 1. Why is it in my little loading circle? That usually doesn't happen. Anyways. And then the other one that we said is the square root. So anything inside the square root must be greater than or equal to 0. Because if it's less than 0, then it's a negative number, and you can't take the square root of a negative number. Else you get an imaginary number. So, okay, so just add 2 to both sides. X is greater than or equal to 2. So that's one last restriction we have on this. Whoops. And there we go. So now we just take this and then put it in a form that, it wants. And it looks like, oh, wait, I wrote that wrong. It is not equal to, it is greater than or equal. There we go. Uh, okay, so, well, we know that A, B, and C are all wrong because they want to, go all the way down to negative infinity, but we know that it must stop at -2 and be greater than it. So, I'm not -2, just regular 2. So it must be greater than that. So, uh, these ones say it anything below that is okay. It goes all the way down to negative infinity, but it can't. So it's not any of those. Uh, and then actually, if we kind of think about it, uh, 0 and 1 are both less than 2. So, I mean, we kind of don't really have to worry about this one at all because they're both less than 2, and we said that x must be greater than 2. So we just kind of doubly defined that it can't be equal to 0 or 1. So we just have to worry about this one. And our options are these two. Now they look really similar, but the one thing that's different about them is this one has a bracket and this one has a parenthesis. Whenever it has a bracket, that means it includes the number. So you're saying, if there's a bracket, you're saying that uh, x can equal whatever number is there too. So it can equal 2. And if it's a parenthesis, then it can't equal 2. It's saying that 2 is disallowed. So if we look back here, this is a greater than or equal sign. So yeah, it can equal 2. So it ends up being the first one. So D, that's our answer. All right, question 2. You have a function here, and it's asking for the difference quotient, which is literally just for all of these for this f of a plus h and for this f of a, you just f of a is this. So you just plug that in, simplify everything. Whoops, I dropped my pen. There we go. And then you'll get it in the form of one of those. So let's do that. So this f of a plus h, if we plug in a plus h in place of x, we'll end up getting, let's see, let's write this a little smaller because this is going to be big. That'll be a plus h squared minus a plus h plus 4. And then, okay, so that's that part. And then for the other minus f of a, that ends up being no, not x squared, a squared. A squared minus a plus 4. And remember, we're doing a minus of all of this because that's what it was in the original. It was a minus. And then all divided by h. I'm gonna leave that out for now. The like putting a divide by h under all of these, that's gonna get a little annoying. So we'll just remember to divide by h at the very end. So we'll keep that in mind. And then, okay, so now we simplify this a plus h squared. That becomes a squared plus 2ah plus h squared minus a minus h. That's the minus a plus h plus 4 minus, and then so it's minus a squared minus becomes a plus a, and then minus 4. And then we can go ahead and combine like terms. So there's two a squareds here, one plus, one minus, so we can cancel them out. There is one h squared, so h squared. There is, okay, then there's plus 2ah. That's the only term with one a and one h, so looks like we do a minus a and then a plus a, so we can cross those out. We do a minus h and then a plus 4 and a minus 4, so that doesn't do anything. So it's h squared plus 2ah minus h. Remember, we're still dividing everything by h from that. And then that works out really nice because every term has an h in it, so that becomes h plus 2a minus 1. And that is E. There you go. All right, numero tres. Just a solve for x problem. But it's a little weird and complicated because look at how many of these 3 to the x and 3 to the 5 we have. All these exponents with base of 3. So we'll be using our properties of logs and exponents a lot for this problem. But the first thing, we'd probably want to get rid of this negative, or this minus 3. So we'll just add 3 on both sides. So this is 3 to the x times 3 to the 5th over to 3 to the 6th equals 81. So now's the point where it's good to remember this one property of exponents where if they're both the same base, or all three of these are the same base, but I'm specifically pointing out these two. When you divide them, you just subtract their exponents. So this ends up becoming 3 to the x times 3 to the negative 1. Now, I just made a big jump there, so let me actually just give you an example. If you do 3 to the 4th divided by 3 to the 2, 3 squared, so that's just 3 to the 4th is 81, and 3 squared is 9. That ends up becoming 9, 81 divided by 9, which also equals 3 squared. And if you'll notice, 4 minus 2 equals 2. So that's something you can use here. That's what we did use. So this ends up becoming 3 to the x times 3 to the negative 1 equals 81. And then we'll do sort of the same trick, but we're just multiplying, so we add the numbers instead. So this ends up becoming 3 to the x minus 1. So we add x and we add negative 1, so we minus 1. That equals 81. This is a great point to use properties of logarithms now. So if we do log base 3 of all this, and then let me rewrite this as log base 3 of 81, then since the base and the value are both the same, they're both 3, that ends up canceling both of these out, and we're just left with x minus 1. So this becomes x minus 1 equals log base 3 of 81, and this is just the same as 3 to what exponent equals 81. You can manually find this, or if you just intuitive with your exponents, you'll know that the answer is 4. If you do 3 times 3 times 3 times 3, so 3 times itself 4 times, you end up getting 81. We actually just kind of found it up here, but hopefully you're good with your exponents then. Okay, so we're back here. X minus 1 equals 4, so x equals 5. We add 1 on both sides, so that's the answer here. Just get good with your properties of exponents, properties of logarithms, because domain questions and derivatives, they often use a lot of things like that. So it's good to know those. All right, number 4. Which of these 5 functions is not one-to-one? And remember, one-to-one means so this is the opposite. If it's not one-to-one, it means when you draw a function, this is just an example I've done here. If you draw a horizontal line through it and it hits it at multiple points, then it's not one-to-one. So something like this isn't because it hit at 3 different points. A function that is one-to-one is something more like that, where any horizontal line you draw through it, it only hits it at 1 point each time. So something like this is one-to-one. So as you can see, this problem becomes a lot easier if you're comfortable with visualizing different kinds of functions and seeing what they look like, and you can do the line test in your mind or on your paper. But if you're not totally comfortable with doing that, you can just manually plug in a few different points and sort of get an idea of what it looks like, and then that'll work out most of the time. You can see if the line test will work or not. So let's do that for each of these. Let's see, not number 1, A. Let's see, it's square root of 2x. That's a square root function, which is the opposite of a parabola like that. So a square root function will look like that. Actually, it won't even include this bottom part, but even still, this passes the test. It just hits it at 1 point each time. So we know that it is one-to-one, so that's not the right answer. What about B, x cubed plus 2? So we can really ignore the plus 2 since all that I'll do is just move it up 2 units, and that doesn't change its one-to-oneness at all. So x cubed, we know if that looks like this, that's bad drawing, that looks like this, it ends up becoming really close to not being one-to-one because the derivative at 0 is just, or the slope at 0 is also 0, like it is horizontal at this one point. And we know if it dipped any more, like if it was like that, then fails the test. But it doesn't, it's just straight. So any line here, yep, it works out, passes the line test. So it is one-to-one. So we know that's not the right answer. C looks pretty promising. It's a sine function. And hey, what does sine look like? It just keeps repeating this motion forever. And oh yeah, that absolutely violates that test. Look at all these points that it's hitting. It hits an infinite number of its points. And this multiple 5 that it does, that doesn't change anything. It just, I believe that would, it would just, I think it just like squeezes it or lengthens it, whichever way it goes. But that also doesn't change it at all. So yeah, that one is not one-to-one, so that ends up being our correct answer. Since this is more of an abstract problem, let's also run through D and E so we know we have the right answer. E to the negative x, well, we know a regular e to the x looks like this, and a negative e to the x, or not negative e to the x, e to the negative x, uh, that, I believe you just, yeah, that's just this. So the other direction. That still passes the test, doesn't do anything. So that's still one-to-one. ln x is the inverse of e of x. And since e of x is one-to-one, that means its inverse is also one-to-one. So that one's one-to-one too. So we know our answer is C. All right, question 5. Find the inverse of this function and then plug in 1 afterwards. and then we'll get some value. So finding inverses, remember what you do is just, first we're going to rewrite it with a y instead of an f of x. So y equals 1 over 3 plus x, all over 5 minus 2x. All you do is just swap the x and the y. So this y becomes an x, and these two x's become y's. And then do a bunch of algebra to get it back in the form where it's, y equals again. And then whatever's left is the inverse. So let's go ahead and do that. I think the first thing we should do is multiply both sides by the 5 minus 2y. So that becomes x times 5 minus 2y equals 1 plus 3y. And then we could distribute the x into both of these terms. So that's 5x minus 2xy equals 1 plus 3y. And then remember, we're trying to get the y's by themselves, so let's have every term that has a y, let's put them both on one side. So let's add this to the other side and then subtract 1 to put it over there. So that would end up becoming 5x minus 1 equals 2xy plus 3y. And then we could take out a y from the right side to get close to getting it by itself. So that becomes, oops, let's get rid of that. So 5x plus minus 1 equals y times the quantity 2x plus 3, and then we can divide both sides by 2x plus 3, so that's 5x minus 1 over 2x plus 3 equals y. So that's our inverse here, and at this point we can just do f of x, f negative 1 of x, and then it has to plug in 1 into this. So this becomes 5 times 1, which is just 1, minus 1 over 2 times 1, which is just 2, plus 3, which equals 4 over 5. There we go, A. All right, number 6, the halfway point. The altitude in feet of a drone t seconds after it takes off is given by this function. So basically what that means is if a drone starts, so let's draw this out. At the starting time 0, looks like it starts at 4, and then since it's a cubic function, it looks like it's gonna go like that. So looks like the drone, here's a really crappy drone. It starts out, oh, that's not a correct drawing. Looks like it starts out 4 feet above the ground, and then since it's cubic, it slowly rises and rises, and oh god, it's getting really fast. It's going up to infinity. So that's kind of how you can visualize this problem. And then what we're asked is to find the average velocity of the drone over this specific time interval from 0 seconds to 3 seconds after takeoff. So obviously for this, we're going to need to know what our velocity function is, and that's pretty easy to find because we're given the position function. And if you're given the position function, then the velocity function is just the first derivative of the position function. And then in order to find the average velocity over the interval, we do this one function where we plug in the second time interval, the ending, and then subtract the first time interval, and then divide all that by the second minus the first. So this is our part 2 here. Before we do that, we need to find out what our velocity function is. So let's do that. Let's just take the derivative of h of t. So the first element, let's rewrite it so it's a bit bigger. So t cubed over 6 plus 4. Okay, so the first term of our position function, t cubed over 6, derivative, we take the 3, move it out to the front, and then subtract it by 1. So this becomes, so v of t equals 3t squared over 6. 3 over 6 just becomes 1 over 2. And then plus 4, derivative of any constant is just 0, plus 0. So we can leave that out. Okay, so now we have our velocity function. Now we just use this function and plug in these values to get the average velocity over the interval. So v of 3 in the velocity function, that's 3 squared, which is 9 divided by 2, so that's 9 squared. And then velocity at 0, if we just plug in 0, that'll still be 0. So then we have all over 3 minus 0. So really this is just 9 squared divided by 3, which is the same thing as 9 squared times 1 over 3, and that makes it a little clearer to see what's going on. That's 9 over 6, which is 3 over 2 when you simplify it. So there you go. The proper way of saying this is the average velocity of the drone over the time interval from 0 seconds to 3 seconds is 3/2 feet per second. All right, number 7. For the function graphed below, which of the following statements are true? So let's run through these one by one, all 4 of these. Number 1, f of 2 is defined. Yep, yes it is. If we go to 2 and then go up, we find it's defined at 3. So, yep, 1's good. All right, number 2. The limit as x approaches 2 is 3. Yeah, that one is false, actually. No, I'm sorry, it's false. I was about to say true. I was about to say, well, it's defined at 2, so then the limit at 2 is just what it's defined at, which we just said is 3. But we have this big gap here, right? And in order for a limit to exist when there's a gap like that, then the left-sided limit and the right-sided limit both need to equal the same thing. And we see here they're not. The left-sided limit is equal to 3, and the right-sided limit is equal to 1. So therefore, the general limit at that part where there's no like sidedness doesn't exist. So that one's false. So number 3, this is where we're asked a question like that. At the limit as x approaches 2 from the positive side, the right side, equals f of 2. So, well, first off, f of 2 is just equal to 3, so we can just rewrite that as 3. But does the limit as x approaches 2 from the right side equal 3? No, it doesn't. Looks like it's approaching 1, as we just said. So that one's false too. What about number 4? As x approaches 4, or it just exists. The limit as x approaches 4 exists. So let's see. 4, well, there's a discontinuity here, but it's different from the previous limit because it's removable. See how when you approach that point from the left side and the right side, they both approach the same value, which is, looks like it's 4. So in this case, since the left-sided limit and the right-sided limit both approach the same value, the general limit does exist. It's the opposite of 0.2 here. So we know this one is true. So A, B, C, D, E, E. That's our correct answer. 1 and 4. All right, number 8. Calculate a limit. So it's the limit as x approaches -1 from the right side, the positive side. All right, a limit question. So first off, can we simplify this at all? Like, is there any polynomial that we can sort of split up and maybe a difference of squares or just 2 different little terms that we can end up canceling things with? But we don't have one of those. So unfortunately, we can't simplify this. So our next step is what I like to do. Whoops. What I like to do is literally just plug in the limit we're trying to find into the equation. And what we end up getting will determine our next steps. It'll be one of 3 things. So let's go ahead and do that. Plug in -1 on the top. -1 minus 4 is -5 all over. -1 squared is just 1. Negative 1 plus 1 is 0. So this ends up being negative 5 over 0, which is negative infinity. So in this case, where our answer is infinity, we know that our limit will end up being either positive or negative infinity. So we can cross these ones out. And before you just instantly, oh, it's negative infinity, we found our answer. Before you jump to that conclusion, first we keep in mind we're doing it from a side, so it could either be positive or negative at infinity. So and in order to figure that out, we do that sort of number line trick where we make our line, and in the middle we have, whoops, and in the middle we have our limit we're trying to find, and then we find two values surrounding it that are defined, and then we can figure out like, that like plus trick where they're all pluses on one side and all minuses on the other. So something like that, and then we end up figuring out if it's positive or negative infinity. So let's pick two values that are defined in the function. Uh, let's see, negative 2 will work. And, oh, no, let's not do 0 because if we plug in 0 here, 0 squared is 0, and that ends up making our denominator 0 again. So let's not go that far. Let's do negative a half instead. Okay, so then we just end up plugging negative 2 and negative a half into our function. So and when we're doing this, all we end up needing to know at the end of this is its sign. So if it's positive or negative. So we don't have to do all of the calculation, just end up finding the sign of everything. So negative 2 minus 4 is still negative. Negative. Negative 2 squared will yield a positive answer, and negative 2 plus 1 is negative 1, which is still negative. So we see that the numerator is negative and the denominator is positive times negative is also negative. So this ends up yielding a positive answer. So we know that everything to the left of our limit value is positive. Okay, so now we do the same thing for the other side. We plug in negative a half. So again, we're just looking for the signage of everything. So negative a half minus 4 is some fraction that is negative. I don't really feel like figuring out what that is. And negative a half squared is positive. Negative a half plus 1 is positive this time. So looks like our numerator is negative, our denominator is positive. That ends up yielding a negative answer. So we know that everything to the right of our limit value is negative. And from this, we look back to what the direction we're taking our limit from, which is positive from the right side, like that. So we know that the signage of our limit is negative. So we know that our answer is negative a half. All right, number 8, calculate a limit. So it's the limit as x approaches negative 1 from the right side, the positive side. All right, a limit question. So first off, can we simplify this at all? Like, is there any polynomial that we can sort of split up and maybe a difference of squares or just two different little terms that we can end up canceling things with? But we don't have one of those. So unfortunately, we can't simplify this. So our next step is what I like to do. Whoops. What I like to do is literally just plug in the limit we're trying to find into the equation. And what we end up getting will determine our next steps. It'll be one of three things. So let's go ahead and do that. Plug in negative 1 on the top. Negative 1 minus 4 is negative 5 all over. Negative 1 squared is just 1. Negative 1 plus 1 is 0. So this ends up being negative 5 over 0, which is negative infinity. So in this case, where our answer is infinity, we know that our limit will end up being either positive or negative infinity. So we can cross these ones out. And before you just instantly, oh, it's negative infinity, we found our answer. Before you jump to that conclusion, First, we keep in mind we're doing it from a side, so it could either be positive or negative at infinity. So, and in order to figure that out, we do that sort of number line trick where we make our line, and in the middle we have, whoops, and in the middle we have our limit we're trying to find, and then we find two values surrounding it that are defined, and then we can figure out like, that like plus trick where they're all pluses on one side and all minuses on the other. So something like that. And then we end up figuring out if it's positive or negative infinity. So let's pick two values that are defined in the function. Uh, let's see, -2 will work. And oh, no, let's not do 0 because if we plug in 0 here, 0 squared is 0 and that ends up making our denominator 0 again. So let's not go that far. Let's do -1/2 instead. Okay, so then we just end up plugging -2 and -1/2 into our function. So and when we're doing this, all we end up needing to know at the end of this is its sign. So if it's positive or negative. So we don't have to do all of the calculation, just end up finding the sign of everything. So -2 minus 4 is still negative. Negative. -2 squared will yield a positive answer, and -2 plus 1 is -1, which is still negative. So we see that the numerator is negative and the denominator is positive times negative is also negative. So this ends up yielding a positive answer. So we know that everything to the left of our limit value is positive. Okay, so now we do the same thing for the other side. We plug in -1/2. So again, we're just looking for the signage of everything. So -1/2 minus 4 is some fraction that is negative. I don't really feel like figuring out what that is. And -1/2 squared is positive. -1/2 plus 1 is positive this time. So looks like our numerator is negative, our denominator is positive. That ends up yielding a negative answer. So we know that everything to the right of our limit value is negative. And from this, we look back to what the direction we're taking our limit from, which is positive from the right side, like that. So we know that the signage of our limit is negative. So we know that our answer is -1/2. All right, number 11, we're almost done here. At what value of x does this function have a removable discontinuity? All right, easy. So remember, a discontinuity is just whenever it's discontinuous, which is the opposite of continuous. So if you have a graph that goes da da da, and then suddenly it stops, and then picks back up somewhere else, this whole gap here is discontinuous. And it can also be just a single point, like say jumps there and then jumps back up there. This point here is discontinuous. Now, a removable discontinuity is where if you have a graph with a hole and it like picks back up at the same point, then it's removable. So in other words, the left-sided limit and the right-sided limit at the discontinuity both equal each other. So based on this shape that I've just drawn out here, there's only one of those in this entire graph, which is right there at x equals -2. All right, number 12, last one. Hooray. For what values of c is this piecewise function continuous from the right at x equals 2? So, okay, let's just digest this and parse it a little bit. So there's three different definitions for f of x. We have a definition when x is less than 2, when x is greater than 2, and when x is equal to 2. And cool thing is, we're just asked to make it continuous from the right. So whenever it's greater than 2. So we are really just concerned with these two tabloids here. We don't really have to pay much attention to this one up here, the x is less than 2. So what it wants is it's defined at one point that it told us. So when x equals 2, then the function equals 3. It's defined like that. And it says that the function, whenever it's greater than 2, so whatever this is here, is this function with some constant c that we don't know. And there may be one or two constants, there may be one or two values for c that will make this line hit it right there. So all we really need to do is plug in 2 for x right there, and then set the whole thing equal to 3. So let's go ahead and do that. C squared times, see, x would equal 2, so 2 squared plus 2 equals, see, at x equals 2, the function equals 3. So let's simplify and solve for c. So 2 squared is 4, so 4c squared plus 2 equals 3. Let's subtract 2 from both sides. 4c squared equals 1. Move it over here. Let's divide 4 on both sides. So c squared equals 1/4, and then square root both sides. So c equals plus and minus 1 over root 4, which is, oh, why is my eraser not working? There we go. Which is plus or minus a half. And there we go, b. We didn't even need to mess with the original x is less than 2 stuff since we were just asked from the right. So that's pretty nice to have as a last problem on this exam. So congrats. Hopefully you made it all the way. If not, maybe sorted by topic or whatever, and you just stumbled across this one. But for those that watched the whole video, congratulations, you finished an entire exam. So good job.